Welcome back. This is Silvia Mazzoni. In this video, I want to go through just a highlight, but in-depth highlight of all the different little features that I've put into eSEES. So maybe it won't make sense in building a single model, but I just want to make sure that I cover all my bases. I assume that you've already set up the OpenSees path. I'm going to create a new file, and I'm going to call it my full demo. And I'm going to choose where it's going to be. This is the window that tells me where I am. It tells me my home path and where my OpenSees executable is. And I'm going to take this little window and move it to the side and keep an eye on it. So I go back to my model and I'm going to go through all these different options that I have. The first is the pull down menu for the file. If you want to do a new, a load. What a load does, it just reads a input file that you have written and sources it. So you don't have it open, it's just loaded and loads up all the data. If you want, oftentimes I'll do a lot of my editing actually on the script itself. And so then you press reload and source the full demo file, which is the file that I'm working on. And if you want, maybe you've got some additional files that you want to source, so you'll do that through here. Then you can actually click this and it just saves just the materials and components for OpenSees testing, but right now we'll just set that aside. Then you can have the save and the save as, and you can also view the file right as is if you want. But of course that doesn't work. Oh, it does. There it is. So this is the file itself, and the current data one, I haven't done anything yet. So this is just, it has actually just set up the initial templates that it does in setting things up. So I'm going to minimize this and set it aside. Now the input menu is really the place where you do most of your interaction. What's really cool about TickleTK is that these are all just notebooks and they're actually all open at the same time. So you can go back and forth between one and the other. So maybe you're working on a component, realize, wait a minute, I need to add a material. You go, you add the material, and then this gets updated automatically if there's an option for a material, for example. Also, there is the edit and new options. They're both open at the same time. The only one that makes a difference is the elevation. I couldn't get those to work, the edit and the new to be open at the same time. So you're either in the new mode or in the edit mode for the model. Everything else, you're working simultaneously with the two. So let's go through these one by one. File setup. This is something that you set up once, and especially with the units, make sure that you don't go back and change the units, because as the program inputs values, sometimes it actually processes the units. Most of the time, I just go through this dimensionless, but this is a good way of reminding yourself what are the input units. The data gets put into a subfolder of where your file is, and I call it data, but if you want, you can change that itself. And this just tells you where the input file is. So that's just a file setup. I just never even go into this tab at all. I'm always working in inches and kips and seconds. I'm thinking maybe I'll make a default one that is in metric units. If anybody tells me whether it's better to use millimeters, centimeters, decimeters, or meters as the basic fundamental unit. But here you can actually go in and change it. Materials is the fun one. Okay, the materials and the components is the most fun of all these different inputs. So there's a lot of different input materials that I have put into here. And what I've done is I've done a little bit more than just, basic OpenSees input. Actually, I have a lot of default values that I compute for you, but they're not hidden. You can actually go in and edit them. So for example, if we go into the elastic material, the very first one, there's two types of elastic materials. There's elastic and the elastic no tension. So let's go to the elastic material. So, and this is pretty much consistent with all the cases. We've got a set of required arguments. Sometimes if you press plus, it opens it up wider or smaller. It's really hard to predict how big your monitor is going to be. So everything seems a little bit small. So we've got the required argument. Well, the first one is the type, okay? So this sets up what this menu is going to look like, all right? So we've chosen the elastic. This is the label, what you're going to call it. By default, it just uses the elastic. If you've defined one, it adds an underscore 1, 2, and 3, and so on. So sometimes you don't even have to touch this. And then for the elastic, I have E as the tangent, is a required value. So you put in 29,000 or whatever value that you use. I have set up some default values, just fun to just show you what this should look like. So you can click on this. It's actually going to take the default values that I've set up and perform the analysis and show you what the behavior of this material is. So we have E, and then you can actually, in OpenSEES, you can have a different stiffness in the negative direction. Right now, I've set it equal to E. And you've got a $ E because you're telling it to evaluate it. It's not the letter E, but it's the actual value of E. When you do things like this, you got to be really careful. But in those cases, just leave it as to what I have done. So if you want, you can actually say 0.5 times E, and then test it, show me what it looks like, and it's going to run OpenSEES. And you see now that it's got a different value. If you want, you could save it. So let's just save it here. I'm going to show you these in more interesting materials. So I'm going to say save and save this material. It tests it, shows you what it looks like once it's done. So let's go to something a little bit more interesting. I've got lots of different types of materials. There's also the Elastic Perfectly Plastic. These are available in OpenSEES. So there's the EPP and the EPP gap material. I've got different types of concrete, okay? So I've got concrete 1, 2, 3, 4, 6, 7, and 7 confined, because in one of the old manuals I found some additional input for modeling confined concrete with Concrete 07. And then what I've done is I've created a confined and an unconfined concrete, which is really just using Concrete 02, but I will show you. So for example, let's go with confined concrete. All you have to do is put in F'C. Everything else, all the other parameters, I've given you some recommended values. Again, you can go in and change them, or you can just leave them as I have them set. As you can see, I don't use the units here. When you use units, you got to use units all the time consistently. So what I'm going to do is I have 4 KSI concrete, so it's just 4. And I'm going to test it and see what it looks like. And so this is the behavior of the concrete material. I can do different kinds of tests if I want. I can go to a higher strain range. I can even make it that much higher, but this material won't go that far. The testing, you can do full cycles, which is what this looks like. You can just do a pull or push cycles, only one directional. And then you could do a tension or compression cycle. Oh, I'm sorry. So these are cycles in only pull or push, and then this is just unidirectional push. So it's just like a pushover analysis. So the default is full cycle. Some materials have degradations. I've actually set it that it does 3 cycles at each material level. It's always good to see how it behaves. Now, the difference between this material and the unconfined concrete is this residual strength. So this has a residual strength of 0.8. The unconfined concrete has 0.2 or 0.3 or something like that. So I've set things up that you really just need to define what F'C looks like. So I'm going to say save. What we could do is now let's define it. If you want, we can go and change this material itself to adjust it to make it unconfined. I think what I do for unconfined concrete is maybe we could make it 1.0 times. And actually does this updating for you at the same time as you update the values. And then the residual, we're going to make it be 0.3 times. And so here's my new concrete behavior. As you can see, it degrades faster. So if we go to 0.04, you can see that it's definitely a different behavior. What we could do is, so I can say modify, and actually now I'm going to, the other one was confined concrete, so now I'm going to call this unconfined concrete. And I'm going to save it under this new name. Okay, and then what's really cool is, if you want, let's compare the behavior of those two. So I'm going to go to a range of, let's just keep it as is, the default values. So I'm going to copy these data, and if you want, you can even visualize these in a bigger window, and you can keep track of it. So, but I've got copy and paste here. So I'm going to copy these data. Then I'm going to go and I want to look at my confined concrete behavior. Analyzes it. There's my confined, and I'm going to paste the values that I had for my unconfined concrete on top of there. And you can see there's, slightly differences in values here. And I'm happy and I'm done with these concrete materials. Let's build a steel material. So I'm going to then play with reinforced concrete. There's so many different options that you can do with for steel. And this gives us an opportunity to look at these different material types and how I've grouped them. So we've got the bilinear model. The bilinear model, there's 3 different options. One is looking at steel 02 and steel 01, which are purely bilinear, or using the hysteretic material in OpenSEES, but where I've given you just the option for 2 values. And so the second stiffness actually goes on to infinity. So you can pick one of these 2, one of these 3, if you want a bilinear model. If you want a multilinear model, now you've got different options. These are literally, all of these all use the same hysteretic material in OpenSEES. But in this case, you can actually define ductility values. Here you define initial stiffnesses and secondary stiffnesses. And when it says points, you're actually defining the individual points. So I've got the trilinear, the bilinear, quadrilinear. The hysteretic material goes to 4 segments. And then even options for unsymmetric. So anything above that assumes that it's symmetric. So this is pretty much all the different ways you can do the hysteretic material, which I'm a big fan of. Then there's these other steel materials. There's reinforcing steel and then reinforcing steel and just general input. I'm not always successful with this material, but I've put it in here in case you're able to use it in some of your cases. Then I've got these degrading models. These are IMK models, and there's 3 of them. One is what I'm just going to call degrading model, which is the pinching model, which is the one I like of these. And then you've got the option to define it in terms of rotations, so rotation segments, you know, the plastic rotation, elastic rotation. You can define the points, or you can define ductilities, which are the ratios. So it's just different ways of doing the input with this material. What's really nice about this material is you can control degrading. So I'm actually going to use this as my example for my reinforcing steel. Then we've got the bilinear IMK. You've got the peak-oriented IMK, which are just different variations of the same material. I also have some soil springs, the PY, TZ, and QZ simple materials that are actually interesting to play with. You can put them in your soil springs at the base, or if you've got an embedded, you could actually put them at different floors. And then I've got some additional materials, which is the self-centering material. So I've shown you all these different materials. So let's go with the degrading model, which is kind of nice. And I always just kind of go with this one where I define rotations. It's just one place to start versus others. So there I am. And now you've got these different inputs, okay? You've got the optional inputs and you've got the required inputs. Required inputs, as you can see, they're empty. So what I like to do is let's just load up some sample values so it's easier to understand what this input looks like. So I've loaded up the sample values. And this is what the material looks like. This is still in the bilinear range. So hey, why don't we just increase this range a little bit more? Let's go to 0.05. That could be too high, but let's see what happens. Testing that material. Now you see a little bit more about the behavior of this material. So now let's play with it. So Fy is the yield strength, elastic stiffness, the strain hardening ratio in the positive direction, the theta P, theta PC, these are these theta values. And you can kind of play with what these different values are. The one I wanted to show you here, so this is the input. You can play with the input. If we go to the optional values, the very first one, there is the residual strength. But if you scroll down and you go here to rate of cyclic deterioration, this material, you have to look at the manual and poof, you can click it right here and it's going to show you. It's going to open up your browser to that material. And so you can actually get an understanding of what the input, and I have that for all these materials, even though the input is not directly the same as the input there. However, I'm going to play with these, the rate of cyclic deterioration in positive loading direction. And in the negative direction, I have it to be the same. So I'm going to play with this, and this is the slider. Right now, I have no degradation. So let's actually copy these data. Then I'm going to put some degradation. I'm going to test it. So this is really sensitive. So if we put on top the values that I had before with no degradation, it's kind of cool to see how even the envelope of this material reduces significantly. Now, what you've got to do is you got to figure out what options and what input parameters match the type of steel that you're trying to copy. What's really cool is what I've done here is, let's rerun it. You can't copy anymore because there's 2 sets of datas, but I'm going to say test it again, and then I'm going to copy these data, and I'm going to open up Excel, and I can actually paste these into Excel, and you can visualize the data and you can just plot it. So I've done it so that you can put things into the clipboard. And honestly, this is really the only value I play with here, so let's not make it so bad. So let's make it degrade a little bit less. So let's see how much less. I'm copying that data. I'm going to test it. Okay, is this enough less degradation? I'm pasting the previous highly degraded values, and yeah, I don't see too much. Oh, because I'm playing with the residual strength here. That's why it's different. Yeah, you got to be careful. I can't color code everything. So let's make this value that much smaller. Okay, now I have a lot less degradation than I had before, and I'm actually kind of happy. And it's interesting because you can see the degradation not just as a function of displacement, but also between cycles. You can see how it's degrading from one cycle to the next. So I'm happy with this, and I'm actually going to call this my reinforcing steel. With this name, what's really cool is that if you give it this name, you can then go and change and give this steel material a different, even just a whole different model, but then that doesn't change everything in your subsequent definitions because it's always referring to that material by name. So we're done defining our materials. If you want, we can look at the summary to see. And so we've got always a rigid material and a loose material in case I need it in a hinge here or there. But here's what our concrete material looks like. Sometimes you can just use this just to build materials in sections. So here's our unconfined concrete, and here's our reinforcing steel. Good, I'm happy with those. I'm going to actually save my file. I'm going to now build components. We want to do something in reinforced concrete, so let's actually look at the options that we have. We've got elastic components, which are defined just either where you define the E's and I's, or there's some of them that actually compute those values for you. We've got fiber components. So I call them components, which are really because these are not just cross sections. You can use them for moment curvature, moment rotation, or even springs, which is the moment rotation relationships. I've defined some templates for fiber components. I've got a simple rectangular fiber component, reinforced concrete, 2 of them, a few of them rectangular, a wide flange type of shape, a circular with double reinforcement, and a wide flange fiber component where you can customize it yourself and give it some properties. Now, I've also done for the wide flange sections, I have the database, so you can actually get all the elastic properties of a W section, or even define it as a fiber section. So maybe we could put a steel beam on top of some reinforced concrete columns. We could try that. I have the same thing for AISC. I've developed some simple couples for PM interaction in case you want to play with them. And then I've got these springs that you can use as moment curvature, moment rotation. It really depends where you define. So I would always just jump straight to the 3D model where I've got, and you can have a cross section, a concentrated hinge, or just plastic rotation. These are kind of the same type of material and behavior, but then it really depends on if you're going to put them in a lump plasticity element. You've got to use either the plastic rotation or a concentrated hinge. You don't want to use a cross section because it will not do the proper integration. And then I also have nodal constraints where you define pretty much, they're not really springs. You define the springs as fixed or free. So let's define a wide flange fiber section. And I'm going to use the same material as I use for my reinforcement. So what cross section do I want? Well, let's look at a W30 section, and we're going to use my reinforcing steel. So that's what the section looks like. I'm going to test it. And this is what the moment curvature relationship looks like. This is under 0 gravity load. You can actually test it under 0 axial load or different positive, compression or tension. You can actually then scale the maximum deformation. I didn't want to put another scale here. So with respect to what I have set up here, you can actually go farther out, multiply by integer multiples or fractions. So it really depends on your section. So that was the way of giving you full range. Just like you have in the materials, you could do different types of cycles, number of cycles. Don't touch this too much. It doesn't always work. It only works for some fiber sections, but it's there and I forgot to remove it. And you can also test it. This is about this axis, but you can actually test it in the rotated direction, and that's the moment curvature in that direction. So let's go back and test this section. It looks really good. We can change axial forces if you want. You can play with the number of fibers and different properties, but I'm going to just say in these options right now, just let them be. If you want, play with them and see what it really means. So I'm going to save this cross section. Then I'm going to put in, I would like a new section. I'm going to do a reinforced concrete section. So let's put a fiber. Let's do a reinforced concrete rectangular fiber section. I'm going to look at my required components. Of course, I'm going to just do this. It gives you an error because I haven't defined this material here. So I need to make sure that it's using defined material. So I'm going to put reinforcing steel here, confined concrete. It's still giving me errors because I haven't defined those, and unconfined concrete. Now that those materials have been defined, I no longer get an error. So if you want, you could test this section. Ooh, it's terrible. It needs some reinforcement. So let's go in and put some bars here. So we've got the top, and the second layer of reinforcement. So it's got 2 layers of reinforcement and even has some side bars. My default is a number 9 bar. If you want, you could change the number of bars. Yes, it's in the US standard bar sizes. And I'm going to say, look at this. They pop up. I'm going to put that many rebar at the top, and then I'm going to put in that many rebar at the bottom. Okay? Because this is going to be a column, I'm going to actually put a second layer with maybe 3 bars here, 3 bars here, and I'm going to put in some intermediate bars as well. So this is a really nicely reinforced concrete section. I'm going to test it. Oh, a lot better than before. And it's interesting because you see that it is actually degrading because we use the degrading material. So it's really cool that way. I'm happy with this. I can test it and rotate it. So let's copy what it looks like here. I'm going to test it in the rotated direction. And as you can see, it's an almost symmetric section, but not quite. Oh, I love it. It's wonderful. So I'm going to save it. You can play with all these different options if you like. Now what I want to do is the other column is going to be a circular column. So let's go here. We're going to pull out a circular column with double layer reinforcement. Why not? So I'm going to put in my, it's going to be a 36-inch column. My cover is going to be my unconfined concrete. My core is going to be my confined concrete. That in-between core is actually, I'm going to say it's going to be confined concrete. If you want, you can define it an intermediate. And now because I've got 2 layers, I'm going to use the same steel for them though. So reinforcing steel and reinforcing steel. And here's what my section looks like because I've defined it. Look at that. It's got no steel. All right, because by default it has 0 bars. So let's put some bars in the outer layer. And let's put some bars in the inner layer. And let's make the bars in the inner layer just a little bit smaller. So let's put some number 4 bars there. And you can actually see that these are drawn to scale. So maybe they're a little too small. Let's put some number 6 bars. What does this look like? If I test it, oh, it's beautiful. And I might actually get a symmetric section because it's circular. It really depends on the number of bars you have laid out. That's pretty much it. These are all just other options, and I'm going to say save. So I've defined my materials, I've defined my sections, and now I'm going to save my input file. Element types, I'm not going to go into right now. I need to do a whole other section on this. Right now, just go with the defaults, and it's going to be a distributed beam column element, but you can actually, I've set up enough defaults that you can choose them as you go through. Loads, I'm going to just go with the default gravity load, but maybe what you could do actually is let's do an additional load that is going to be the dead load or the live load. Okay, so those are almost like load cases. And I'm not going to touch, you saw that you had options for pushover and uniform earthquake, so those are something that you can play with and see what you get. Let's go over to define our elevation now. So I'm going to do a new elevation. I'm going to keep it simple, and I'm just going to keep it as a simple portal frame. You've seen my other videos that you can actually change this to maybe 80 by 80, and you can change these dimensions. And I'm going to take in now, I'm going to not deal with these elastic sections. I'm actually going to define my beams and columns. So the very first one is going to be my column on the left. So it's going to be my circular column with my double layer. You can actually define it at 3 different parts of your element, but I'm just going to go with the distributed plasticity element here, which is what I'm going with the default. And I'm going to assign that element right here. Now I'm going to change, and now I want to do the rectangular fiber. And you got to be careful because these are now staying with the old ones. So it'd be nice, I'll find the button that makes them be the same. But right now you just have to use that option. I got my concrete section that's going to go here. And then I'm going to do my steel section, W30. W30, W30. If you want, you can define a different section if you have a changing section, and it's going to be right here. If you want, you go down here and you can actually visualize it and say, okay, tell me what the element type is and tell me what the component label is. And those are the 3 options that you have for the 3 different locations. And if you want, you can actually go in here now and say, hey, in the middle node, I actually want something else, but I'm not going to touch that right now. So let's put back my W30. Oh, you can actually go in and do a whole lot of different ones, but I'm going to keep what I had. I'm happy with this. And then you can actually change the orientation from the horizontal axis bending, which is how it was before, to actually rotate it if you like. Different element types, we should have done that when we defined it. I'll let you play with those. I'm happy with my portal frame. I need to define gravity loads, and I'm going to put in a distributed gravity load for the default gravity case of 10 right here. And then I'm going to put a live load of 100 at these nodes. And I'm happy. I'm going to save this. I'm going to now build a grid. I'm going to do a grid. It's a simple case, so I don't know what values I was using there. This is going to control the 3D model. So I'm keeping it square, but could be anything you want. And now let's define our 3D model here, where my grid is going to be what I had before. Yes, I do need to work on my graphics. And I only have 1 elevation, which is easy. So I'm going to put in my elevation here, here, and here. I'm actually going to leave a little bit of eccentricity here. And I do want my rigid diaphragms though. Lots of other options, but I'm going to go. You can play with this. You can rotate it. You can visualize different parts of it. So because those are fiber sections, you can actually visualize what the cross sections look like in scale. So I think I put columns that are a little too big. But that's all right. Show the local z-axes. It's something I just define it from node I to node J, and then you could see here what the local axes are going to be. I take care of all that for you, so you don't worry about it. These are going to be your node tags and element tags. And if you want, we can display the rigid floor. And this actually tells you what the different elevations that I'm using are. I don't know what this does, so I'm going to let it be. I'm happy with my model. I'm going to click save. And I'm always going to save my file here. Now, analysis models, I trust myself to define these properly, but you can then go in and change them. Load combinations is what I want to play with, because I have a default gravity load combination, but as you could see, we actually brought in the live load. So I'm going to do full gravity. Do not use spaces. Okay, and then I'm going to put in add the default gravity and add the live load. But on the live load, I'm just going to put in a factor of 0.5, but I'm going to leave inertial factor of 1. So these are, if you do your dynamic analysis, you can think about a little bit on how these work. If you don't want to think about it too much, then use the same value as there. Now, I'm happy with this. This is going to be my full gravity and gravity only. So maybe I'll say gravity only. And I'm going to save it. So now what I want to do is I want to add a pushover analysis. So I add a transit analysis, which is going to be a pushover analysis. And I wanted to go maybe to a maximum of 5 inches. And I could have played with these options when I defined the pushover load, but I kind of like having a basic pushover load and then change some of the details here, which is why I've left it here. See, right now I could change even the direction to be in the Z direction, but be careful because then you can't use it in a 2D analysis. I want to do a full cycle, and I'm going to do, let's do 3 cycles each one. And so maybe let's do 2 inches and 5 inches, okay? I put a space 2, space 5. That's going to be the displacement increment. If you want, I can do, well, maybe what I should do is I should go to 2 inches with a displacement increment of 0.1. And then what I'm going to do is I'm going to do a pushover. You can't mix different types, but you can actually just keep on adding cycles, where now this is going to go to 5. And it's a full cycle again. Maybe I'm going to do 3 cycles here. And my displacement increment is going to be 0.1 actually. And I'm happy with that. So I'm going to call this full gravity pushover. And I'm going to save it as such. Again, I'm going to go and save my file. Now I'm ready to do my analysis. A summary here kind of shows you all the different things that I've defined. I think if you look under miscellaneous, you can actually view all that in its own window. But right now, let's just keep moving with this. I'm done with my input. Let's go to analysis. So I've got elevations and grids. So these are different options for viewing different things that have labels. Don't worry about them right now. These are the models that we can analyze, the 2D frame or the 3D frame. And then let's just analyze both. And then we've got 3 different combinations. By default, it does a default gravity only, so it's only that load. But we want to do a full gravity and a full gravity pushover analysis. Let's visualize the modes. I think modes 1 through 3 are good. And here you can actually scale the modes. Right now I've got a scale factor of 10. That should be enough. So let's just try it and see what happens. So click here, step away, and let OpenSees do its thing. Here's the 3D, and here are the mode shapes for the 3D analysis. As you can see, I kind of scale the deformations a little too high, but this is just good feedback on trying to understand what these different mode shapes look like. I haven't given you too much control on the sizes of these things, so maybe someday I will. So you go and you click here and you press enter. I'm happy with what I've seen. Here is the second load combination. Pushover has the same gravity loads. So what I do is I define the masses and I actually perform a gravity analysis, and then I perform a eigenvalue analysis, because that's really kind of where you want to be, is what are the properties of my structure after gravity is applied, but before any sort of lateral load is applied. So I'm happy with this. I click on the OpenSees window and close it. So now let's just go ahead and run the analyses, and I'm going to just bet it all and run all the models that I want. The way this runs, it's going to run them in sequence. If you want to run them in parallel, all you have to do is just open up multiple instances of this and make different selections. I'm working on something else, but I've got to make sure that it works properly first. What I recommend you do actually at this point is you go over here, and I forgot to look at the communications, okay? So this is what the program was telling us during these analyses. When you define your models, oftentimes when we do a 3D analysis, there's some conflicts because we've already defined certain elements, like the column elements. And what you got to remember is it always goes with the first definition of that element. So you should be okay. So here's the different results that we have from the different analyses. There's some cases where it won't be able to compute higher degrees or higher modes. That's why it didn't show them to us, because it was an error, because in the simple portal frame, it only has one dynamic degree of freedom, and we asked for 3. So if you reduce this to go from 1 to 1, we can actually visualize the mode shapes for the 2D, which is really just a simple mode shape. So this is really helpful to tell you what's going on if there were any errors in the analysis. Again, I'm going to put it on the side. I'm going to go ahead and run these analyses, make sure I've got all the loads I wanted to do. Yes, you can just generate the OpenSees input files, and we've gone through that. So click here and sit back and kind of watch the analyses. Gravity analyses go by real quick, and now it's doing a pushover in the 2D portal and frame. You can actually watch the OpenSees output, but it's going to get dumped into a log file that you can visualize later. And here it's plotting the force displacement. Remember, we asked for a number of cycles to 2 inches and then to 5 inches. So you pretty much sit here and watch it do its thing. As you can see, the structure is not really going to go too far beyond the 2 inches. So I got a little bit ambitious on this. It's very important to keep in mind that this displaying of the deformed shape slows your analysis down significantly, maybe even tenfold. So what I like to do is, okay, well, my first kind of analyses, I'm going to watch it, and then when I run a batch of analyses, then I'm going to turn this off. Same thing with watching here, the force deformation. This is really just plotting a displacement of one of these nodes versus time, where time in a static analysis is proportional to the base shear. So it's a good way to look at the hysteretic response of your system. If you stop the OpenSees analysis, you're messing with the system, and it's going to give you an error, but if you want to, you can. You just kind of click OK. What the program wants to do is when the analyses are run, it actually is going to do a lot of processing. And so that's where you may get the errors. But if you have to stop it, which is why it's always good. I recommend to start with something a little bit less ambitious than what I started with here. Kind of nice to at least know where you are in the analysis. You can watch it, which is a good thing when you've got degrading models. It's not as easy to watch it when you have a non-degrading model. The time history analysis is kind of nice because you can actually watch the time history. So maybe I will run that analysis next. It's done. Now it's processing that analysis. It's going to take all the data and reformat it into new files that are a little bit easier to read for the program in the post-processing visualization. Now it's going to grab it in the 3D. That's a lot faster. And now we start our pushover in 3D. So what I've done here with these visualizations is you watch the 3 different planes, the ZY plane, XY plane, and the ZX plane. In my global coordinates, the Y is always vertical. I chose that so that your elevations are consistent with your 3D model. I know a lot of people like to use the Z as your vertical axes, but I kind of like using Y because it's consistent for both 2D and 3D. So this is the deformed shape, and then a nice little perspective. These are all just OpenSees display recorder. What you see on the left is the force deformation response in the x-axis and in the z-axis. And even though we are forcing the displacements, is displacement controlled in the x direction. It's really cool how you can watch it degrade. In the z direction, you actually do get some forces and displacements, of course, especially because we have some eccentricities in the system. I want to show you while it's running an analysis. I want to show you this little window. Even though you can't really view it during the analysis, you can't scroll up and down while it's running the analyses, but this shows you that what was output in the echo file actually gets dumped into here. And you'll see it, and then it tells you some of the data and how long the analysis took in the post-processing. So I'm going to put it back away. Here we are at 5 inches. Interestingly, very similar behavior than we had in the 2D, which kind of makes sense. If you look at this view on the bottom left, it's actually, it's the ZX plane, so you can actually watch it as it deforms from above. This is the loading that we're giving it in the X direction, the cyclic positive and negative, and then you can actually see the eccentricity that is causing this to actually see some motion in the two directions. So otherwise it should just look like that. That's the input file that I have, and you will see a lot of these are the different cases for each model, and each model goes into its own folder, and then within the folders you've got model data and you've got the different types of analyses. This was a different demonstration, but it's the same thing as what you have here. And you'll see these are the OpenSEES input files, and this is actually the log. This is what I put out, so with a lot of puts commands, but also if there were errors, or for example, well, this is a warning that I actually give you. So any communication for OpenSEES comes there, and then this is what an OpenSEES input file will look like that is generated by the program. And you can see there's all the typical input for OpenSEES, and it's actually pretty well documented as well. So you can go off if you want and take these input files and modify them to what you need. Interesting to see what the response is in the Z direction. If you look at these deformations, you see this dot here. This node here is because we have rigid diaphragms definition. This is actually the master node that I am actually plotting and controlling for the pushover analysis. And the program itself does everything you need for rigid diaphragms. And right now it just does it for the floor, so it's pretty straightforward and easy to define. It's done with the analysis, but it's still processing now. Depending on the size of your model, this can take a long time, and this is something that I need to work on to change on just the post-processing. Not very efficient, not the best way to store memory. But this is what I come up with as an idea a long time ago. There it is. It's done. Here's all the output that we have. In brackets is what OpenSEES output from the analyses. So I'm going to minimize this. Now we're ready to look at the results. So let's go to results. And let's just jump straight to this case. So this is the 3D frame model and the full gravity pushover analysis. We can see our force deformation here, and you can actually go through all the different points here. And right now I'm visualizing deformations. So we were starting with 0, and you can actually watch it cycle. This really depends on the speed of your computer and the processing power it has. If you want, you can turn on and off different elevations if you only want to visualize one of them or two of them. And I think the program needs to catch up with me. If I want, I can look at bending moment diagrams as well, and you'll see that these bending moment diagrams changes depending on where you are in your loading. So if we're down here, those are going to be pretty low values, but large deformations. If you want, we can set these deformations to 0 if you want to just visualize the bending moment diagram. We can watch curvatures. I think that's always the best thing to look at. These are curvature values. Maybe I could scale. They're actually the length of the plastic hinge. And right now, this is at very low loading. If we do it here, you'll see that the values change. Right now, curvatures are pretty low. In that case, here we actually see pretty high curvatures. If you want, you can tell it, okay, only show me the elements with these levels of curvatures. And you can do this with all the other forces. Now let's look at the response. We can go here and we can say, okay, I want to look at the element response. And here it is in front. So this is our steel section. I'm going to set it aside for a second. I'm going to pull out a concrete section. Oh, here's the other rectangular section.